Hi everyone, this is pre-class video on module 5 power system stability. Myself Dr. M.J. Chandrasekhar, Associate Professor, Department of EEE, SAB Institute of Technology. In this video I will be explaining the equal area criterion concept. This equal area criterion concept can be used for quick prediction of the stability. This method is based on the graphical interpretation of the energy stored in the rotating mass as on A to determine if the machine maintains its stability after the disturbances or not. This method is only applicable to a one machine system connected to an infinite bus or a two machine system, because it provides physical insight to the rotor behavior of the machine. We know that the power angle equation, the swing equation for a single machine, it is written m d square delta over dt square is equal to pi minus pe, and this pi minus pe is nothing but the difference in the powers from the input and the output. So, this because of the accelerating power it comes. So, here d square delta over dt square is equal to Pa minus m. Here m is constant and the delta value variation is mainly depends on the accelerating power. See, here we have written the swing curve. Swing curve is a plot of variation of delta with respect to time. As you see here, initially the machine is at some speed, for that delta naught you will be getting, and if delta value varies unboundedly like this, then it is unstable. If delta value increases and oscillates and comes to some steady state, then we say that the system is stable. So, the stability aspects you can analyze by having the swing curve. Next, we will see how the equal area concept can be implemented for finding the stability. So, what we do is, as we know, we have d square delta over dt square is equal to Pa by m. So, let us multiply 2 times of d delta over dt in both LHS and RHS. In the equation you will get d delta over dt and 2 times of Pa by 2 times of d delta over dt. So, this can be written as 2 d dt d square delta over dt square is equal to 2 times of Pa over m, this is constant, and d delta over dt. So, integrate with respect to the time on both LHS and RHS, integrate. So, integration differentiation get cancelled, we will get d by dt whole square will get is equal to 2 by m, 2 get cancelled here. So, 2 by m into integration of delta naught to delta Pa into d delta. So, upon integration we get this. So, as you know, the differentiation of x square is 2x into dx by dt. So, this can be written as in the LHS you can write like this, 2 by m integration of delta Pa into So when PA, here PA is nothing but Pi minus PE. This is the accelerating power. Delta naught is the initial torque angle or the power angle before the rotor begins to spin because of the disturbance. So when it is doing so, when it is swinging, d delta over dt is equal to 0, then this equation becomes integration of delta naught to delta PA d delta is equal to 0. For stability, the area under the curve, see here the area accelerating power area should be equal to 0. So that means, see here we have considered the power angle curve. Okay, it is the plot of the electrical power output with respect to delta. So as we know, for a non-salient pole machine, it is like this. So this is the delta 1, delta 2, and this is delta naught. Delta naught is the initial torque angle. So when we take the delta 1, see here delta 1 A, B, C. So here area 1 and area 2, if the areas are same, then it comes to equilibrium, then the system will be stable. So for stability, the area under the graph, so that is A2, area under the graph of accelerating power versus delta must be 0 for some value of delta, that is the positive accelerating area under the graph must be equal to the negative area. So A1 is equal to A2. When we do so, this criteria is therefore is known as the equal area criterion for stability. So when both these two areas are same, then it is stable. So this is the curve PE. PE is P max into sin delta. Now this concept let us apply to the sudden changes in the power input. See here power angle curve, as we are seeing the electrical power output with respect to delta. So here as you see, initially it has delta naught, and as you change the load, then it is shift to delta 1 and delta 2. So we have to adjust this value of delta 1 in such a way that the areas area 1 and area 2 should be same. So in the above figure, the point A corresponding to the delta in the initial steady state operating point, at this point the initial power to the machine, that is Pi naught is equal to Pe naught, that is this is Pe naught, where Pe naught is the developed power because of the input power. When a sudden increase in shaft input power occurs to Pi, so that is the synchronous machine, and here this mechanical power input, and you will get the electrical power output. If there is a small change in the electrical power output, the accelerating power becomes positive, and the rotor moves towards the point B. Here B is there. So if you increase the delta value, then electrical power output also increases. So the area 1, area 2. So area 1 is delta naught to here, delta naught to delta 1, that is PA. PA is nothing but Pi minus PE. Here Pi naught minus P max into sin delta. P can be written as P max into sin delta. P max into sin delta. P max into sin delta into d delta. So next area 2 is from here to here, delta 1 to delta 2. This is delta naught, this is delta 1, this is delta 2. So delta 1 to delta 2, P max into sin delta minus Pi, okay, from here to here. So, with this you can write Pi into Pi into delta 1 minus delta naught plus P max into cos of delta 1 minus cos of delta 2 but Pi is, as I told you, P max into sin delta. When we substitute this equation, we get P max delta 1 minus delta naught sin delta plus P max cos delta 1 minus cos delta naught. Apply the limits, upper limit minus lower limit, with Pi is P max sin delta, we get this delta 2 into sin delta plus P max cos delta 1 minus cos delta 2. So, this equation becomes delta 2 minus delta naught sin delta 1 plus cos delta 2 minus cos delta naught is equal to 0. So, this equation becomes delta 2 minus delta naught into sin delta 1 plus cos delta 2 minus cos delta naught is equal to 0. So, this means both the areas are same, then the system is stable. Next, we will see the effect of critical clearing angle and critical clearing time. So, critical clearing angle is the angle at which fault has been removed and at that time the fault is cleared. So, if the fault occurs in a system, delta begins to increase under the influence of the positive accelerating power, and the system will become unstable if delta becomes very large. There is a critical angle within which the fault must be cleared if the system is to be remain stable, and the equal area criterion is to be satisfied for that condition. This angle is known as critical clearing angle. For that, let us consider the single machine connected to infinite bus. Here generator is connected to infinite bus through the transmission network. Here generator side transformer and circuit breakers at the starting and end of the transmission line, and here at this junction HT side of the transformer there is a fault. How to analyze this? As you see here also I have considered the initial torque angle delta naught. For that the mechanical power input is Pe, and corresponding to that the electrical power input here is Pe. And if the delta increases, the delta value increases, suppose if there is any sudden fault happens, then it goes to the point D and then E. So, here area 1 and area 2, area 1 is more compared to area 2. The expressing area 1 is equal to area 2 mathematically. So, we can get this equation, that is Pi delta C minus delta naught is equal to delta C delta 1 Pe minus P1 into d delta. So, let us have the equations to analyze this. So, Pi delta C minus delta naught is equal to integration of delta C to delta 1 P max into sin delta into d delta minus Pi delta 1 minus delta C. Here Pi delta C minus Pi delta naught is equal to P max minus cos delta 1 plus cos delta C minus Pi delta 1 plus Pi delta C. This can be written as P max cos delta C minus cos delta 1 is equal to Pi delta 1 minus delta naught. Here P max is sin delta naught. So, you substitute these these two equations, we get P max cos delta C minus cos delta 1 is equal to P max delta 1 minus delta naught into sin delta naught. So, cos delta C is equal to cos delta 1 plus delta 1 minus delta naught into sin delta naught. Here delta C is the critical clearing angle and delta naught is the initial power angle and delta 1 is the power angle to which the rotor advances beyond delta C. For a three-phase fault with PE is 0, then d square delta over dt square is equal to pi of Pi by h, that is the swing equation. So, integrating the above equation here, so twice, and utilizing the fact that d delta over dt is equal to 0 for stable condition, then we get delta. So, double differentiation of this, we will get delta pi of Pi by 2h t square plus delta naught. Then P max into cos delta C minus cos delta 1 is equal to P max delta 1 minus delta naught into sin delta naught. So, here cos delta C is equal to cos delta 1 plus delta 1 minus delta naught into sin delta naught. So, here delta C is that clearing angle, delta naught is the initial power angle and delta 1 is the power angle to which the rotor advances beyond delta C. So, for a three-phase fault with the P is equal to 0, we can get that d square delta over dt square is equal to pi of Pi by h. So, utilizing twice, so delta we get pi of Pi over 2h t square plus delta naught. So, with this we can write the delta C, this is pi of Pi over 2h Tc square plus delta naught. So, here the clearing time, critical clearing time is given by 2h delta C minus delta naught whole divided by pi f into Pi. This is the expression for critical clearing time. So, the power angle curve is the electrical power output versus delta. So, here area 1, area 2, if these two areas are equal, then d delta over dt is 0, then we can get the stable condition. We will see what are the factors affect the power system transient stability. So, to improve the power system transient stability, so first one is improved steady state stability by higher the system voltage levels. We can improve the transient stability, and additional transmission lines if you have, then it will be good, it will improve the steady state stability. Smaller transmission line series reactance and smaller transfer leakage reactance, series capacitance transmission line compensation, static VAR compensators and flexible AC system fact devices, and high speed fault clearing and high speed reclosure of circuit breakers. If we have, we can avoid the transient stability, and single pole switching, fast responding high gain exciter, and breaker resistors. These are the factors affect the transient stability. With this, I will be ending this video. Thank you.